Welcome to my solved examples video for module 3. I'm going to be working on a second example here. Just to recap from the first one we did, I asked you guys to work with y prime plus y equal to 0, and you solved it using the power series method, and that was the solution. And you all realized that that's nothing but c e to the minus x, because if you solve y prime plus y equal to 0, you have dy over y equals minus dx. So ln of y equals minus x plus c. So y equals to ce to the minus x. So you could have solved that anyways, but you notice that you solved the power series method and you still got e to the minus x if you recognize that this is e to the minus x, or it's the infinite series expansion for e to the minus x. So let's move on to a more interesting example, a bit more complicated. This is example number 13 on your PowerPoint. So I'm going to be looking at y double prime plus x squared y prime plus xy equal to 0. And we will only be dealing in this module with homogeneous differential equations, FYI. So let's look at it. It's obviously not Cauchy-Euler, so let's try to use the power series solution method. And here you notice that your p of x and your q of x, I mean the coefficients here, are both analytic at x equal to 0, meaning they're differentiable and continuous. And they're not undefined at x equal to 0. So therefore x equal to 0 or x not equal to 0 is an ordinary point here, which means I can use y equals the summation of an x minus x naught, which is 0 to the n, as n equals 0 to infinity. So I could use that series expansion to find a solution, which is just simply x to the n. Of course, x naught equal to 0 obviously is the most preferred point, ordinary point for us to write our solutions about, but sometimes they don't work. But most of the times they do, especially for ordinary differential equations that could be solved with ordinary points. Anyhow, so let's find the appropriate derivatives here. So y prime will be the summation of n x to the n minus 1 as n goes from 1 to infinity. And my, let me erase this x not equal to 0. Okay, and then my y double prime will be n times n minus 1 an x to the n minus 2 as n goes from 2 to infinity. So these are my y prime and y double prime. So let me now substitute these into the given differential equation. I'm going to put that in yellow. So that's my given differential equation. All right, so let's substitute my y double prime and y back into the yellow. So y double prime, I'll have summation of n minus 1, an xn minus 2 as n goes from 2 to infinity, plus, now notice that my y prime is being multiplied by x squared, so I have to add 2 to that power when I'm actually writing x squared times that. So that'll be the summation of n equals 1 to infinity of n x to the power of n minus 1 plus 2, which will be n plus 1. So this will just be n plus 1 because we added 2 to the power. So that'll be n plus 1. And then plus xy, so again, I'll write the y, which is n equal to 0 to infinity, an x to the n, but there's an x behind there, right next to it. There's an x here that has to get multiplied to the x on the inside. So that power just becomes n plus 1, because it's just 1x there. And that's equal to 0. Now, in order for us to find all the constants to our solution, to our power series solution, I need to combine these three power series and then try to take the coefficient, set it equal to 0, and find all the constants. Now, as mentioned before, our first step is to plug in the first index of each power series into the power of x and check out the power. So starting with the first one, if I put 2 in the place of n, you get x to the power of 0. So if I go to the second power series, I replace n with 1, I get x squared. And if I go to the third power series and replace n with 0, I get x to the power of 1. So for all the x's to start at the same power, I need to take out the first two terms out of the first one, and I need to take out one term out of the third one. So let's do that. So I'll start with n equals 2. So I'll have the summation. Actually, let me just write the constants first. So n is equal to 2, 2 minus 1, a sub 2x to the power of 0. That's the first term. Take out the second term, so that means n is equal to 3. So plus 3 times 3 minus 1, a3, x to the power of 3 minus 2, which is 1, plus the rest of the power series, which is now, and I took out n is equal to 2, n is equal to 3, so now I'm at n equals to 4. Let you see that for a second. Okay, so I'm at n is equal to 4, and I write the rest of the series as is, n minus 1, an x n minus 2. Okay, so the second one's already at x to the power of 2, which is the highest, so that's the one I just keep without touching. So that's n equals 1 to infinity, n x to the n plus 1. Okay, and then the third term, I need to only take out one term. So that means n is equal to 0. So if I take out the first term, a0 x to the power of 1, and plus, I write the rest, which starts at 1 an x to the n plus 1 equal to 0. I'll let you look at this for a second. Okay, so let me clean this up a bit, put things together. So let's see, I have, I'm looking for the non-power series terms. And so I want to put those together, and I'll put the power series together. So let's start with a naught x to the power of 1 plus 2 minus 1 is 1, 2, so you get 2a2, and x to the power of 0 is 1, plus 3 times 3 minus 1 is 2, 6a3x to the power of 1, plus, and I'm not going to write this because I want to still work with that side, plus the 3 power series equal to 0. So I'm going to keep the power series on ice here, trying to combine the constants or the non-power series terms. So I have 2a2 plus, and I have an x1 common here, so I have a naught plus 6a3 x1. So I've combined the two together now, so my constant's 2a2, and the coefficient of x, which is my first term, is a naught plus 6a3. And now I write the other 3 power series here, plus, and let's see where we at. 1, and goes from 4 to infinity, an x to the n minus 2 plus n x to the n plus 1 plus an x to the n plus 1 equal to 0 as the n goes from 1 to infinity, and this one is also n goes from 1 to infinity. So that's what I've got so far. Let you sort this out for a second. Okay, so now it's time for us to look at try to combine the power series here. So just by looking at the non-power series terms, remember I need to make the left-hand side equal to 0. So here, in order for this to be 0, never mind the power series at the moment, just looking at the first couple of terms, 2a2 has to be 0. Has to be, if the whole thing has to be 0, even if the power series are all 0, and even if the x to the power of 1 term is 0, it doesn't matter. In order for this thing to be 0, 2a2 has to be 0. So also, a naught plus 6a3 has to be 0. Same reason. Because even if everything else is 0, if that's not 0, it won't be 0. So it has to be 0 for our sum of a and x to the n to be a solution. So that must be true. Okay, so now I need to do the same thing with the power series. I need to find out what makes that 0. So that means I need to add them together. but in order to add them together, they have to have the same index and the same power. So again, we start playing the give and take game. So let's see. At this point, you look at your three power series, and it really, there's no magical or sort of systematic way to do it. It's really just a mental trial and error type of a thing. So so let me see. I have two n plus 1 powers. So, and I have an n minus 2 power, almost majority. So if I wanted to turn I have two n plus 1s. So based on majority, I'd kind of thinking about turning n minus 2 to n plus 1, which means I have to add 3 units to that. So if I add 3 units to that, it'll be n plus 1, which will match the powers. And I have to lower the index by 3 units, and that will turn that into a 1. Oh, and that will work. So let's try that. So I'll start the first power series. So I'm going to lower the index by 3 units, so 1 to infinity, and I'm going to increase the argument by 3 units. So I'll get, let's see here, I'll get n plus 3, n plus 2, an plus 3, and x to the power of n minus 2 plus 3, which is plus 1, plus this one is as is, and so is this. Because all I need is the indices and the powers of x to match. Okay, so now I'm in a position where I could combine the three power series. So I have n is equal to 1 to infinity. And now I take the coefficients. I have n plus 3, n plus 2, an plus 3, plus n an plus an. And if I factor all that out, times x to the power of n plus 1 equal to, that must equal to 0. Let you catch up to that one. All right, so now remember, again, that's one of my conditions. That's another condition. And here now, I know that in order for this to be 0, the only way that could happen is for that to be 0. So that's my third condition. And do you wonder why these conditions at this point? And I just want to remind you, because people keep forgetting this, students keep forgetting this, that at this point, what are we looking for? Remember, you're looking for this. Y equals a naught plus a1x plus a2x squared plus a3x cubed plus, and all the a's thereafter. See, that's what you're looking for. So in reality, you're looking for the sequence of, you're looking for a naught, you're looking for a1, a2, a3, and so on. So in reality, that's what you're looking for, because once you have that, then you have the solution, because you already know what the solution is going to look like. So therefore, all these conditions I'm talking about, condition 1, condition 2, and the main condition, condition 3, these are all to help me find these constants. I hope that clarifies it, because at some point you kind of lose the fact that what am I looking for, so you know that's what you're looking for, because once you have the a's, then you have your solution. Okay, so let me erase this and continue. It's just a note. Okay, so now I need to take my third condition and set it equal to 0. So I have n plus 3, n plus 2, an plus 3, plus, and if you look at the an's a constant, so I could just n plus 1 an equal to 0. And I always want to solve in terms of the higher value. So if I solve for n plus 3, I'll have minus quantity n minus 1 divided by n plus 3, n plus 2, an. And there's my so-called recursive relation there. So you need, and so you have condition 1, condition 2 in yellow up there. And now here's my official third condition, the third equation I'm going to be using to find the rest of my constants or coefficients. So then once I have that, then I have my solution. I'll let you catch up to this. Great. So now let's again take values for, and let me just label this as well. Call this the recursive equation. I don't care about the names, but I'll call it condition 3. It's what they call the recursive equation. Okay, so now let's take different values for n and try to figure out the rest of my constants. Now remember, going back, let me write that here. I know that 2a2 equals 0, which means a2 must be equal to 0. And then from the bottom one, I have a3 is equal to minus 1/6 a naught. So those are my two conditions from above. And again, remember my objective here is to find all the A's. So there's two of them there. Okay, so let's see. Now if n is equal to, I have a3, so I can't let, I mean, it would be redundant for me to let n is equal to 0. So I'll start with n is equal to 2. So that'll give me, actually, sorry. Okay, n is equal to 1. That'll give me a4. Because I have a3, so I need to get a4, so I need to start with n is equal to 1. So a4, and that's what I start with. So a4 equals minus 1 plus 1, 1 plus 3, 1 plus 2, a1. So a4 becomes minus 2 over 4 times 3, a1. Right. So this becomes minus 1/6 a1. So that gives me some sort of a formula for a4, or what a4 is going to be. Now remember, this is a, let me go back to the very beginning, right there. Remember, this is a second order differential equation. Now if you're dealing with a second order differential equation, and I'm just going to write it here, okay, erase it. If you're dealing with a second order differential equation, you're expecting c1 y1 plus c2 y2 as a solution because it's a second order. Remember that. So now here we're trying to find these two y's using power series. So we are completely expecting that it's going to be some kind of, so there are going to be two constants used here. So you're not going to find some values for two constants of specific values. So two constants are going to be used to write all the other constants. So almost like parametric equation where t is used for both x of t and y of t. So here I'm obviously expecting, when I'm trying to find all my a1, a2, a3, a4, a5s, it's quite natural to see that all the other a's, a4, a5, a6, a7, a8, all the subsequent a's, all going to be in terms of either a naught or a1 or two a's. So therefore, that first a, let's say a naught, would represent the first constant, and the second a, which is like a1 that keeps repeating, represents the second constant, and then I'm going to be looking for two solutions that are going to be coming out of the power series. So that's quite expected here. Anyways, let's move on. So that's a4. Now if I go to the next, so n is equal to 2 now, so a5 equals negative 2 plus 1, 2 plus 3, 2 plus 2, a2. So this gives me, yes, that's right, a2 is 0. So no matter what this is always 0. Very good. Now if I continue, my n is equal to 3, a6 will be negative 4, right, times 6 times 5, because if you look at a pattern, a3. Because remember, we're going for A1 to A2, so you can see the pattern. You don't really have to keep calculating it every time. And here you're going from 4 and 3, and then you're going to 5 and 4. So obviously the next one will be 6 and 5. So you really don't need to see this recursive relation to be able to figure out what the numbers are going to be for the constants. You could just look at the pattern. Okay? And what's the terms of A3? But what's A3? A3 is minus 1/6 A0. Right? So if I multiply all that out, my A6 will be 1/45 A0. You could verify this yourself. And same, if n is equal to 4, I'm going to do the same thing, A7, but I'm going to skip the formalities. I know the answer, so 252 A1. So that's enough constants for me to calculate. See, I could write the solution now. So let's see if I can start. So my y is equal to A0. Now my A0 is just A0. There's nowhere that says A0 is anything like a particular value. So A0 is just A0. So A0 plus A1x. Now my A1, I see that most of my constants are being written in terms of A1, so A1 is another constant that's just going to have to exist, so everything is written in terms of it. So the two pillars, the two bases, basically, are A0 and A1. All right, so A1 exists as well, so A1x plus A2x squared, but what's A2? Well, A2 is 0, right there. So this becomes 0x squared. Okay, the next term is then a plus or minus. Let's see. So we says plus will be x to the power of 3, correct? Right. So let's see what the next term is, which is A3. So my A3 is minus 1/6 A0. So it will be minus 1/6 A0, and that's A3. That's A2, that's A1, that's A0, so I don't lose track. That's always a good idea when you're writing the solution. And then plus, and the next one will be x to the fourth, and this is my A4, so let's go try to find what A4 is. A4 is here, it's minus 1/6 A1, so it's minus 1/6 A1, correct? And then the next term is A5, so it's x to the fifth. Let's go see what A5 is 0, so that'll be plus 0. And then the next term is x to the sixth. That's my A6 term. So let's go see what A6 is. It's 1/45 A0. So plus 1/45 A0. And then plus the next term is x to the 7. That's A7 term, which is 5/252 A1. X to the power of 7, and so on. So now I notice everything is being written they're either 0 or they're being written in terms of A0 and A1. So now if I factor out an A0 and combine the terms, and factor out an A1 and combine the terms, I'll end up with my solution, y equals, so if I pull out the A0, I have 1 minus 1/6 x cubed plus 1/45 x to the sixth plus dot dot dot, the rest of them plus, and it's all in terms of A1 after that. So if I pull that out, I'll have x minus 1/6 x to the fourth plus 5/252 x to the power of 7 plus dot dot dot. And that's my solution. So you see, again, you notice is C1 Y1 plus C2 Y2. Here, my C1 is A0, my Y1, there's my Y1. It's not closed form, but you'll see the power series, the first three terms, and you could look at it. It could be something that you've seen before. You could write it in a compact form. And, C2 represented by A1, and here's your second function. So there's your solution.